Okay, are you ready to explore some really intricate math?
Absolutely.
Today we're diving headfirst into the world of branching random walks
Specifically, their
in
intersections.
eight-dimensional space.
Yeah,
We'll be using this paper as a guide.
intersections of branching random walks on Zell.
Sounds pretty complex to me. Where do we even begin?
Well, it all starts with something called the infinite invariant tree.
Okay.
It's basically an endless tree
Hmm.
with a central spine and branches extending infinitely on both sides.
Like a family tree that just keeps branching forever.
Exactly. Now imagine a particle moving randomly along this tree.
Okay.
Each time it reaches a fork, it can split into multiple new particles,
Ah.
each taking its own random path. That's a branching random walk.
So it's replicating itself at each intersection,
Yeah.
creating this cascade of new particles.
Yes, spreading out across the tree.
Okay, I'm with you. So
And the question is, if we have two of these branching random walks.
on two separate trees.
Yeah. Yes, happening independently on two separate infinite trees.
No.
What's the probability that their paths will intersect?
So we're talking about the likelihood of these randomly moving particles colliding.
Yes, in this vast 8-dimensional space.
I bet the answer isn't simple.
You'd be right, it's not a straightforward answer.
So what is it?
Well, the paper shows that the probability of these paths not intersecting behaves like a power of the logarithm of the number of steps taken.
I think you lost me in the jargon there.
Oh,
Can you maybe rephrase that?
sure. Basically, the more these particles branch out and wander around,
Okay.
the less likely they are to bump into each other. And the rate at which that probability decreases
Yeah.
is tied to the logarithm of how many steps they take.
So there's order to how these random walks avoid each other,
Yeah.
even in this crazy eight-dimensional space.
Yeah.
That's so cool.
It is pretty amazing.
How do the mathematicians even figure this out?
Well, they use some pretty high-level tools. One of them is Green's functions, which help us understand the long-term behavior of these random walks.
Green's functions? Green's functions. Wait, I think I remember that. From university. It's all coming back to me now.
I bet you're a little rusty, though.
Just a smidge.
Well, imagine trying to predict where a drop of food coloring will end up in a glass of water.
Okay.
Green's functions let us do something similar for random walks.
Instead of water molecules, we're tracking these randomly moving particles on our infinite trees.
Yes, exactly. And the paper looks specifically at how Green's functions decay in 8-dimensional space.
And this rate of decay tells us something about the likelihood of intersection.
Yes.
So the faster those Green's functions decay, the less likely it is for the random walks to intersect.
You got it. It's like this. The Green's function represents the influence of a particle's starting point on its future location. The faster that influence fades away.
The faster the Green's function decays.
Exactly.
Okay, got it.
The less likely it is for two independent walks to feel each other's presence and intersect.
That makes sense. Like the farther apart those drops of food coloring are, the less likely they are to mix together.
Exactly.
Okay, I'm with you.
And in 8 dimensions, that's where the logarithmic relationship emerges.
So Green's functions are a key piece of this puzzle.
Yes.
But the paper mentions another term, the depth-first queue process. What is that?
That's a really clever way to represent the structure of our infinite tree as a simple sequence of numbers, like taking a long sentence and breaking it down into words.
So we're making a code for the tree
Yeah, you could say that.
to analyze it mathematically.
Yes. The researchers can then rephrase certain aspects of the problem in terms of simple random walks, which are much better understood.
So we're simplifying things.
Yes, but in a way that still lets us solve the problem.
That's really neat. But how does this simplification help them tackle the actual problem of intersections?
Well, by representing the tree as a sequence of numbers, they can use this sequence to track the movements of those random walks. It lets them analyze the probability of those walks meeting at specific points within the tree.
So they're looking at patterns within a sequence of numbers instead of random walks on a complex tree. That's clever.
It is, and that's how they pin down that relationship between the probability of non-intersection and the logarithm of the number of steps taken.
We've just started to scratch the surface, haven't we?
Yeah, we've got a lot more to uncover.
This is already blowing my mind. Okay, I think our listeners have had a minute to digest all that.
Hopefully their brains aren't too fried.
You promised me a magic formula.
I did, didn't I?
Let's get to it. What's so magical about it?
Well, this formula connects the probability of those walks never intersecting to another cool concept. The number of times the future of one walk crosses paths with the past of another.
Wait, hold on. How can the future of one be related to the past of another?
It's tough to wrap your head around.
They're supposed to be independent, right?
They are independent, yes.
Okay.
But this formula reveals a hidden connection between them through probability.
Like those historical events, seemingly unrelated.
Yes.
But there's a hidden link when you look closer.
Exactly. This formula is that lens, letting us see these hidden connections.
Okay, I need to see this formula
All right.
to really understand. What does it look like?
It's written like this. E1A1BLN.
Okay. I'm not a mathematician.
Right, sorry.
You have to explain that.
Of course. So E represents the expected value of what's inside the brackets, essentially, the average outcome over many repetitions.
Like flipping a coin, we expect heads half the time.
Exactly. And those terms inside 1A, 1B, and ln, they represent specific characteristics of our branching random walks.
Okay.
Think of them as conditions.
So it's like saying we want the expected value under these specific circumstances.
Precisely. So 1A, that's an indicator function.
Meaning?
It takes the value 1 if a certain event occurs and 0 otherwise.
Okay.
1A is 1 if our two branching random walks, one spanning both past and future, the other just the future, don't intersect at all.
So if those walks cross paths, even once, 1A becomes 0.
Yes. You got it.
Okay.
Now, 1B works similarly. It's 1 if the future portion of a branching random walk doesn't touch its starting point after its initial step.
So once you leave home, you can't go back.
Yeah, something like that.
Okay, that makes sense.
And lastly, we have N.
What does that one represent?
NN is the total number of times the future portion of one walk visits a location occupied by the past or future of the other walk.
So it's measuring the overlap between the walks.
Exactly, even if it's not a simultaneous intersection.
Okay, got it.
And what this magic formula tells us is that the expected value of the product of these three terms, 1A, 1B, and ln, equals 1.
So their expected product stays the same.
Yes, it remains constant.
Even though the individual values can change.
Exactly.
Because of the randomness.
Right.
That's interesting.
And this simple equation has huge implications for understanding how likely those random walks are to avoid each other.
It's like a key to understanding them.
Yes.
But we can't just use this formula as is, can we?
No, not exactly. We need to manipulate it to say something meaningful about the probability of non-intersection.
I bet that's where it gets really complicated.
It does get a bit technical, but the paper walks us through it.
Okay.
One of the first things we have to do is prove that this term ln, the number of intersections, tends to cluster around a specific value.
Okay.
Mathematically, we say that ln is concentrated.
So even though those walks are random, the number of times they cross paths is not completely random.
That's right.
Interesting.
And to prove this concentration, we break down the random walk into smaller segments.
Like analyzing a marathon mile by mile.
Yes,
To
exactly.
make it easier to understand.
Precisely. By breaking it down like this, we can apply that depth-first cube process we talked about earlier.
Right, turning those trees into something we can analyze.
Exactly. And then we can rephrase the problem in terms of simply random walks, which are much better understood.
So we're simplifying again. Very clever.
It's an elegant approach, for sure.
But this is just one piece of the puzzle, right?
Yes, it is.
We still need to connect this concentration of ln to the probability of non-intersection, don't we?
We do, and that's where the true power of this formula comes in.
Okay, I'm listening.
By proving that ln is concentrated, we can essentially treat it as a constant in our calculations.
Even though it's technically a random variable.
Yes. It simplifies things significantly.
Okay, that makes sense.
And then by rearranging the formula and using some other math tricks,
Okay.
we can establish an upper bound for the probability of non-intersection.
What does that tell us?
It tells us that the probability of those two walks never crossing decreases at a rate proportional to 1 ln.
Where n is the number of steps.
Precisely.
So the more they wander, the less likely they are to collide.
Exactly.
And we have a formula to describe it.
We do, but remember, it's just an upper bound.
Right.
Yeah.
You need a lower bound, too, to box it in.
To get the complete picture.
Exactly.
The lower bound. Okay. How do we find that?
Well, remember those indicator functions?
1A and 1B.
Yeah, those guys. They're a little tricky.
How so?
They create some dependence between the terms in our formula.
So it's hard to isolate the probability of non-intersection.
Exactly. To get around this, we need to get a bit creative
Okay.
with how we analyze the trees.
What do we do?
Instead of looking at the whole tree, we're going to divide it into sections.
Sections.
Yeah, based on how far each part extends from the origin.
Like chopping it up.
Kinda, yeah.
Oh.
We'll analyze the parts close to the origin
Okay.
separately from those farther away.
To control that dependence you were talking about.
Exactly.
It's like we're breaking down a complex machine.
Yeah, to understand each part.
And then we can find the lower bound.
Well, we have to consider all the possible intersections between these sections
Right.
and use some probability tools.
There's the bounds and inequalities.
Yeah, all that good stuff. And then we get our lower bound for the probability of non-intersection.
So we're basically creating a safety net.
That's a good way to put it. We don't want to underestimate the probability.
Right, of course.
And here's the amazing part. Both the upper bound and this lower bound,
Yeah.
they end up decreasing at the same rate, proportional to one line.
So we've trapped the actual probability.
We have.
Between two functions that are shrinking at the same rate.
Yes.
As the number of steps increases.
Exactly. And that's the big takeaway from this paper.
That's incredible. It's like we've pinned down this tiny probability in this huge 8-dimensional space.
It is pretty remarkable.
It's amazing what you can do with math.
It really is. And this result shows a connection.
A connection.
Yeah, between branching random walks in 8 dimensions
Okay.
and simpler random walks in 4 dimensions. They both have this logarithmic decay.
So there's a pattern across dimensions,
There seems to be.
suggesting a deeper principle at play.
Yeah, and that's what makes this research so cool.
It's not just solving a problem, it's about finding deeper connections.
Exactly.
But we're not quite done, are we?
Not quite.
We still have branching capacity to talk about.
Yes. Branching capacity. It's a way to measure how effectively a branching random walk explores the space.
So how much ground it covers.
Basically, yes. It considers the geometric spread and the probabilities.
So it's a more complete picture.
You could say that. And the paper establishes a weak law of large numbers for this branching capacity.
In meaning,
We can predict its long-term behavior.
as the number of steps increases.
Exactly.
So we're forecasting its growth.
Yes.
Okay.
And in 8 dimensions, it grows at a specific rate related to the logarithm of the number of steps.
That logarithmic pattern again.
It's everywhere.
It seems fundamental to all of this.
It really does. And this discovery about branching capacity is applicable to so many fields.
Like what?
Oh, computer science, physics, finance, even biology.
Wow, that's incredible. It's amazing how these abstract math concepts can have such broad applications.
It's the beauty of math, I guess.
Well, that was an incredible journey.
We covered a lot of ground today.
Infinite trees, 8-dimensional space, magic formulas. Who knew this could be so fascinating?
I told you it would be interesting.
You were right. To our listeners, we hope this deep dive has inspired you to explore the amazing world of mathematics. Until next time. All right, so today we're diving into the world of branching random walks. I know it sounds a little complex, maybe even a bit sci-fi, but bear with us.
Definitely.
It's fascinating stuff.
Yeah.
You provided us with some seriously dense excerpts from a research paper,
Yeah.
Intersections of Branching Random Walks on Z.
Mm-hmm.
And we're going to unpack it. Expert speaker, are you ready to geek out a little bit on some advanced math?
Absolutely. I think this paper is a goldmine of fascinating concepts.
Okay, so for our listeners who, maybe don't work with mathematical theorems on a daily basis,
Yeah.
can you give us a high-level overview of what this paper is trying to achieve?
Yeah, so in essence, it's trying to understand the probability of 2 branching random walks intersecting in 8 dimensions.
Okay.
So imagine a tree-like structure growing infinitely in all directions, and it's randomly splitting at each point. Now picture 2 of these infinite trees overlapping in 8-dimensional space.
Okay.
The paper wants to calculate the chances of those trees ever touching.
8 dimensions. I'm already getting a headache just trying to visualize that. Why 8 specifically?
That's a great question. So 8 dimensions is a critical threshold for this type of problem. In lower dimensions, the walks are almost guaranteed to intersect. But as you add more dimensions, the space increases so dramatically that the chances of them colliding become really, really small. 8 dimensions is right on that edge where things start to get interesting.
Okay, so it's like that tipping point where the probability of an intersection just completely changes.
Exactly.
Got it. The paper delves into something called branching capacity. What is that and why is it important here?
So imagine you're trying to contain a branching random walk within a certain boundary. Branching capacity essentially measures how likely it is to break free from that confinement. What the researchers discovered, and this is really cool, is that this branching capacity is directly related to the probability of 2 walks intersecting. The more likely a single walk is to escape a boundary, the higher the chances of 2 walks bumping into each other.
That's really interesting. It's like saying a tree with really aggressive growth is more likely to get tangled with another one that's nearby.
Yeah.
So how do they actually go about proving this connection mathematically? This is where the paper gets really, really dense.
It does. But the elegance of their proof is remarkable. One of the first things they do is introduce this concept of a magic formula. Now, it's not some kind of mystical incantation or anything. It's an equation they derive that relates the probability of the trees never intersecting to the number of times they do intersect.
Hold on. So you're looking at two sides of the same coin.
Mm-hmm.
How do you connect those two seemingly opposite ideas?
That's the beauty of it. The formula itself is deceptively simple. The expected value of the product of two specific terms equals 1. One term is an indicator function, which is basically a signal that lights up if the past of one walk doesn't intersect with the other, and the future of the first walk avoids 0. The second term counts the actual number of intersections.
So one is like, did they absolutely not touch in this very specific way? And the other one is like tallying up every time they do. That's wild.
And by proving that this relationship holds, they lay the groundwork for showing that the number of intersections isn't just random chaos. It actually concentrates around a specific value.
Okay, so there's a method to the madness of these 8-dimensional trees constantly colliding. They're not completely unpredictable.
Yeah.
But how do you even begin to calculate something like that?
So they use a variety of mathematical tools, including something called Green's functions. You can think of these as functions that provide information about the probability of a walk reaching a certain point. By cleverly analyzing the Green's function for these branching random walks, they're able to prove that the expected number of intersections is proportional to the logarithm of the number of steps taken.
So the longer these walks go on, the more likely they are to intersect.
Exactly.
And we can even get a rough estimate of how many collisions to expect just based on how far they've traveled.
You got it. And that is a big deal because it establishes a quantifiable link between the growth of these walks and their likelihood of intersecting. But they don't stop there. The paper goes even deeper into proving the probability of the trees never intersecting at all.
And that's where things get even more interesting, right?
Yeah.
Because dealing with infinite trees, even mathematically, seems incredibly complex.
It is. To tackle this, they introduce this really elegant simplification technique. Imagine drawing a circle around a portion of these infinite trees. What they do is they analyze the sections of the trees inside and outside of that circle separately.
So instead of trying to tackle this massive infinite structure all at once, they're breaking it down into manageable pieces.
Exactly.
Yeah.
And by carefully selecting where to draw that circle and using the properties of random walks, they're able to essentially decorrelate different sections of the trees, making the problem a lot more manageable. It's like untangling a complex knot one strand at a time.
That's what I find so fascinating about these deep dives. We get to see the ingenuity and the creativity behind these mathematical proofs. It's not just brute forcing your way through equations. It's about finding elegant solutions to these really complex problems.
Yeah.
And this is just the beginning. They go on to use these insights and these techniques to derive even more profound results about the non-intersection probabilities. So they've broken down these infinite trees into these smaller chunks. How do they then use that to figure out the overall probability of these trees never actually intersecting?
So this is where their mathematical toolbox really comes in handy. They use some pretty powerful tools like sharp inequalities, which are essentially ways of bounding probabilities.
Yeah.
And they compare them to other simpler random walk problems.
Okay, so instead of trying to calculate this probability directly, which with infinite trees sounds impossible, they're finding ways to say, okay, we know it has to be smaller than this value and bigger than this value.
Precisely. And by making those boundaries tighter and tighter, they get a really good grasp on what that probability is, even without directly calculating it. What they find is that both the upper and lower bounds for the probability of no intersection are proportional to 1 over the logarithm of the number of steps taken.
Okay, so break that down for me.
Right.
What does that actually tell us about how these random walks behave?
So it means that even as these walks grow incredibly large, and remember we're dealing with infinite trees, the probability of them never bumping into each other decreases very slowly. It doesn't just plummet to 0 immediately, which you might kind of expect.
Wow.
It's like these walks have an uncanny ability to almost touch without ever actually doing so, even in 8 dimensions.
That's really interesting. That's wild.
Hmm?
So they managed to wrangle infinity into this somewhat predictable framework. And they don't stop there. They also delve into something called a weak law of large numbers for branching capacity.
You're right, there's more. Remember how we talked about branching capacity as a measure of a walk's tendency to escape those boundaries? This law of large numbers basically tells us that even though the branching capacity can fluctuate a lot in the short term, as the walk gets longer and longer, the average branching capacity starts to converge to a particular value.
So even though each individual step is random, there's this hidden average that emerges in the long term.
Precisely.
Interesting. It's like finding order in the chaos.
Exactly. And it gets even more interesting. The average value that the branching capacity converges to is directly related to that constant we talked about earlier, the one that pops up in the probability of no intersection. It's like they've found this hidden link between these two separate properties of branching random walks.
This is what always gets me about math. You find these unexpected connections between these different concepts. It's almost like you're uncovering some deeper truth about the universe.
Absolutely. And remember, we've been focusing on 8 dimensions because that's what this particular paper focuses on, but they also look at the behavior of these walks in other dimensions, which leads to even more intriguing results.
Like what? Give me an example.
Well, one interesting result concerns the non-intersection probability of a one-sided branching random walk and a two-sided branching random walk.
Okay.
So picture a one-sided walk as our typical tree branching infinitely in one direction.
Got it.
Now imagine you take 2 of those trees and you glue them together at the roots, and now you've got this two-sided walk sprawling infinitely in both directions.
Okay, I'm picturing it. One reaching out to infinity and the other one with its branches on either side.
Yeah.
What happens when those two types of walks interact?
So they prove that the probability of these walks never intersecting is, again, proportional to 1 over the logarithm of the number of steps, very similar to our 8-dimensional case. Basically, no matter which way these trees are growing, the odds of them successfully dodging each other still decreases really gradually.
So even with these wildly different shapes, that core probability relationship still holds true.
It does, but it gets even more nuanced. They also prove that if you just look at the past of the two-sided walk, so imagine like chopping off half of that double-sided tree and you compare it to a one-sided walk, that same relationship holds. The probability of no intersection is still proportional to 1 over the logarithm of the number of steps.
So even with half of its branches gone, this two-sided walk still behaves in this surprisingly predictable way.
Yeah.
How do they even begin to prove something like that?
They use some really, really clever mathematical tricks. Remember that idea of weighting the trees based on the number of times they hit 0?
Yeah.
They bring that back into play here.
Okay. How does that weighting work again?
Essentially, they show that you can compare a branching random walk to a weighted version of itself that's been manipulated so that it never hits 0 at positive times. It's like you're adding these imaginary weights to the tree to kind of guide its growth away from 0.
So it's like a way of simplifying the problem by making one of the trees behave in a very specific way.
Exactly. And by using this clever weighting technique, along with carefully analyzing how different sections of the tree contribute to that overall probability, they're able to prove this result about the non-intersection of these one-sided and two-sided walks. It's a beautiful example of how abstract mathematical tools can unlock these really deep insights into these seemingly chaotic systems.
Yeah, it really is amazing how they're able to take this concept of a random walk, which seems like inherently unpredictable, and reveal these hidden patterns, these hidden relationships. I mean, it really highlights the power of math to find order in these systems that seem completely chaotic.
Absolutely. And the techniques they use in this paper, like strategic simplification, clever comparisons, and powerful tools like Green's functions and weighted walks, these aren't just limited to branching random walks, right? They have implications for a whole range of mathematical problems and potentially even applications in other fields.
Okay, now you're speaking my language. I was hoping we'd get to so what of all of this.
Yeah.
Where else could these insights be applied in the real world?
Well, you could think about population genetics, for example.
Okay.
Imagine trying to understand how a genetic mutation might spread through a population over many generations. Each new generation is like a branch on our infinite tree with a random chance of inheriting that mutation.
Okay.
By applying these principles of branching random walks, we can actually start to model and predict how those genetic traits might propagate.
So from abstract 8-dimensional trees to understanding the building blocks of life itself.
Exactly. And it doesn't stop there. Think about the spread of a computer virus through a network, or even how information or misinformation spreads on social media. These are all processes that you can start to model using similar principles, potentially allowing us to develop strategies to contain those outbreaks or to better understand how information flows.
This is what I find so fascinating about mathematics. It's this ability to connect these seemingly completely disparate fields and reveal these underlying patterns that really kind of govern so much of our world.
I completely agree. And it's important to emphasize that this paper is just the tip of the iceberg. Their exploration of these branching random walks in 8 dimensions, particularly their proofs around those non-intersection probabilities, opens up a whole new avenue of research. It challenges some of the classical mathematical tools that we've relied on and pushes us to develop new approaches for tackling these really complex problems.
It's like they're exploring this completely uncharted territory in mathematics, and their discoveries could have ripple effects throughout the field and potentially beyond.
Precisely. And as we continue to push the boundaries of our understanding, who knows what other hidden connections, what other magic formulas we might uncover.
Well, expert speaker, this has been an amazing deep dive. I think we've gone from trying to wrap our heads around infinite trees colliding in 8 dimensions to uncovering these really profound insights about probability randomness and the interconnectedness of these mathematical concepts that just seem so unrelated. I don't know about you, listener, but my mind is thoroughly blown.
It's always a pleasure to delve into these fascinating areas of mathematics, especially with such an engaged audience.
Absolutely. And to our listener, we hope that this deep dive has sparked your own curiosity about the hidden mathematical wonders that are all around us. Keep exploring, keep questioning, and who knows what incredible insights you might uncover. Until next time on The Deep Dive.
All right, folks, get ready to fire up those neurons because today we are diving headfirst into some serious high-dimensional math.
Yeah, buckle up.
But don't worry, we've got plenty of real-world analogies to keep us grounded, I promise.
Right, we'll guide you through it.
We're tackling this wild research paper on something called intersections of branching random walks on Z.
Catchy title, huh?
Yeah, exactly. If you say it real fast, it almost sounds like
Like a magic spell. But it's all about understanding those patterns you get. When random walks, well, they get a bit more unpredictable.
Okay, so instead of just kind of wandering around aimlessly, these walks are branching off at every single turn, right?
Exactly.
Like a choose-your-own-adventure novel with infinite possibilities.
Imagine every step the walk takes, it creates a new copy of itself, each heading off in a new direction.
Okay, so that's the branching part of the random walk, and this paper wants to know, what are the odds that 2 of these sprawling branching paths are ever going to bump into each other? And this is all happening in 8-dimensional space, right?
Right, that's the big question.
8 dimensions. Now, that's where I have to start using both hands to count, and it still doesn't make sense.
It bends the mind a bit.
Why 8? Is that like the cosmic number for these random walks or something?
Well, it all comes down to this idea of the critical dimension.
Critical dimension.
Yeah, see, in lower dimensions, like imagine just 1 or 2 dimensions, these branching random walks, which we'll call BRWs from now on, just for,
For sanity's sake.
Yeah, exactly. They're almost guaranteed to cross paths eventually.
Okay, makes sense.
But then you go to these super high dimensions, like, hundreds of dimensions, and it's almost impossible for them to meet.
So they're more likely to bump into each other if there's less space and less likely if there's more space.
Exactly, but 8 dimensions, that's where things get really interesting.
Oh, so 8 is right on the edge.
It's the tipping point, yeah, where the probability of them not intersecting,
Yeah.
well, it becomes this really fascinating mathematical puzzle.
Okay, so 8 dimensions is where things get really interesting for these BRWs.
It's the sweet spot.
But hold on, before we dive into the probability stuff, can you just back up for a second? What does critical dimension actually mean?
Sure, absolutely. So picture this. You drop a pebble into a pond, right?
Okay, can visualize that.
The ripples spread out, yeah.
Yep.
But the further out they go, the weaker they get.
Right, they kind of fade out.
Yeah. So in math, we can actually measure that fading influence, that ripple effect, using something called a Green's function.
Green's function, all right?
It tells you how much impact something has at a certain distance.
So the Green's function is like the strength of the ripple at different points in the pond?
You got it. That's the analogy.
Okay, I'm with you so far.
So now imagine that the higher the dimension of your space is, the faster those ripples fade away.
Oh, interesting. So it's like the pond is somehow absorbing the energy of the ripple more quickly if it's in a higher dimension.
That's a great way to think about it.
Okay, I think I see where this is going.
Because in 8 dimensions, those BRW ripples, they fade in a very particular way, a very specific way that makes the whole question of their intersections, well, Super intriguing.
So by figuring out how these walks avoid each other in this critical dimension, we're actually uncovering something fundamental about the way they behave, even in other dimensions.
Exactly. We're getting to the heart of their behavior.
That's pretty cool. So how'd they do that?
Well, this is where the paper gets even more interesting.
All right, hit me with it.
They actually managed to calculate the probability of these walks not bumping into each other.
Wow, they put a number on it.
Yeah, and it's not just some random number. It turns out it's directly connected to something called the logarithm of the number of steps in the walk.
Hold on, logarithm. My high school math teacher is probably cringing right now. What does that even mean in this context?
So think of it like this. Each step of the walk is like a branching point, right?
Okay, like a fork in the road.
Yeah, it's a doubling of possibilities. So the logarithm is basically telling you, roughly speaking, how many doublings it takes to reach a certain number of possibilities.
Interesting. So if you have a higher number of steps, that means a higher logarithm, which means a higher chance of these BRWs bumping into each other.
Not quite. Actually, it means a lower chance of intersection.
Wait, really? So the more steps they take, the less likely they are to cross paths.
Exactly.
That's kind of counterintuitive.
It is. The math shows that in 8 dimensions, the more those walks branch out, the more effectively they're able to spread out and avoid each other. It's
Like they're trying to get away from each other as fast as possible.
exactly.
So this connection they found, this link between the probability of not intersecting and the logarithm of the steps, that's telling us something about the overall shape these walks take in 8 dimensions.
Exactly.
But what does that even mean? The shape of something in 8 dimensions, I can barely imagine 4.
I know, right? It's definitely a head scratcher.
Like, do they look like giant cosmic donuts or something?
Well, we can't exactly visualize 8 dimensions directly, but the math lets us see a kind of shadow of their behavior, you know?
Right, like a glimpse into this higher dimensional world.
And what this research reveals is that in 8 dimensions, BRWs, they tend to spread out in a way that's just more efficient at avoiding overlaps than in lower dimensions.
So they're not just wandering around randomly. There's actually some kind of structure to their chaos.
There's a hidden structure, yeah, and that's what makes it so fascinating.
A hidden structure to their chaos. I like that. That's got to be tough to analyze, though, right? I mean, if these walks are branching at every single step, isn't that incredibly hard to keep track of?
Oh, absolutely.
It's not like each choice only affects the next step. It's like it ripples through all those future branches.
You're exactly right, and that's what makes this research so impressive. BRWs don't have what we call the Markov property.
Markov property. Okay, you're going to have to explain that one.
So basically, the Markov property means that the future only depends on the present.
Okay.
It doesn't depend on the past.
It's like amnesia?
In a way, yeah. But these BRWs, they have this long memory. Every choice they make affects the entire future of the walk.
Oh, I see. So it's like in those choose-your-own-adventure books where making one choice doesn't just affect the next page, it changes the entire course of the story, right? Creates a ripple effect through all those branching storylines.
A perfect analogy.
Yeah.
And that's what makes these BRWs so tricky to study.
So how do they do it? How do you even begin to analyze something so complex?
Right. It's like trying to predict the ending of a choose-your-own-adventure book when there are infinite pages. But these researchers, they're clever. They use some really ingenious mathematical tools to wrangle these unruly walks.
Ingenious, huh? All right, well, I'm hooked. Let's unpack those tools. So how do they even begin to analyze something so complex? What kind of tools do you even use to wrangle a choose-your-own-adventure with infinite pages?
Well, one of their key strategies was using something called a depth-first queue process.
Okay, now you're just messing with me, right? Depth-first queue process.
It sounds way more complicated than it is, I promise. Think of it like this. Imagine you're trying to organize a giant, chaotic family reunion, right?
Okay, I'm with you.
And you need everyone to line up in a single file line, youngest to oldest.
Gotta have some order to the chaos.
Exactly. So that's essentially what the depth-first queue process does. It helps impose order on that branching chaos, and that lets them track the lineage of each branch, analyze the relationships between them, all that good stuff.
So by organizing the chaos, they could actually start to see patterns in how often these BRWs intersected.
That's the idea.
Fascinating. Now, the paper also mentions something called Lemma 2.3, and they even call it a magic formula. That sounds promising. What's so magical about it?
Yes, Lemma 2.3, this is where things get really elegant, because this formula, it manages to connect these seemingly totally different aspects of the BRWs.
Okay, like what?
So we're talking about the probability of intersections, right?
Yeah.
But it also connects to the frequency of visits to a single point. And even the Green's function we talked about earlier, all linked together.
Whoa, it's like finding a mathematical Rosetta Stone.
That's a great way to put it. It's this powerful tool that allows for a much, much deeper analysis of how these BRWs behave.
And that leads to a fascinating concept they call branching capacity, right?
Exactly.
Branching capacity. Okay, you're going to have to break that one down for me.
All right, so remember how the greens function? It measured the influence of a walk at a distance.
Like the strength of the ripples in our pond analogy.
Exactly. Perfect. So branching capacity, think of it like measuring the total spread or influence of the entire BRW, not just one little ripple.
So it's not just about where those individual paths go, but it's a measure of how effectively they explore that entire 8-dimensional space, right? Taking into account all those potential branches.
You got it. That's exactly it. It's a way to quantify the overall, reach of these branching walks.
And this research actually gives us the tools to estimate that branching capacity.
Yes, and that's a big deal.
Okay, I have to ask, this is all incredibly cool, but why go through all this effort to understand these, abstract walks in 8 dimensions? Are there any real-world applications, or is this purely a mathematical mind game?
Well, that's the beauty of math, isn't it?
What is?
Often, the most abstract concepts, the ones that seem the furthest removed from reality, they end up having these surprising applications in completely different fields.
Okay, you've got to give me an example. How could something like BRWs possibly relate to the real world? Okay, you've piqued my curiosity. Give me an example.
Okay, so you know how sometimes the most obvious connections are the ones we overlook?
Sure, like right in front of our noses.
Exactly. Branching random walks, they're actually used to model all sorts of real-world phenomena.
Really? Like what?
Well, they pop up in fields like epidemiology.
Epidemiology.
Yeah, they use BRWs to study how diseases spread.
Oh, wow, I never would have thought of that.
Each person infected is like a branching point.
Right, they could infect multiple other people.
Exactly. And you can analyze the spread using the same tools we've been talking about.
So figuring out things like how likely is it that 2 different outbreaks are actually connected? Or how far could a single case potentially spread?
You got it. And it's not just epidemiology.
No. What else?
They even use them in finance.
Finance. How so?
Well, the stock market, for example.
Oh, right. Unpredictable. Constantly fluctuating.
Exactly. Very chaotic. And BRWs can help us understand and maybe even predict how those markets might behave, assess risks and stuff.
That's wild. So the same math that governs these abstract 8-dimensional walks can also shed light on the stock market.
It's all connected, and it gets even wilder.
Okay, you've got to tell me.
You can even use them to understand how languages evolve.
What a way!
Yeah, each time a word or a phrase branches off, evolves into a new form or a new dialect, that's basically a branching random walk.
Whoa, so the way languages change over time, that's like its own kind of random walk through, vocabulary space?
Precisely. And by studying the shape of those walks, we can understand how languages diversify, how they spread, and how they sometimes even go extinct.
That is absolutely mind-blowing. I never would have thought that something like the branching of a random walk could relate to, the entire history of human language.
It's amazing, isn't it?
It really is. It's like you're telling me there's a secret code hidden in the fabric of reality, and math is the key to unlocking it.
That's a great way to put it. And, the really exciting part is we're only just scratching the surface.
There's more.
Oh, yeah, this deeper understanding of branching random walks. This stuff has the potential to revolutionize so many fields.
Like what? Give me some examples.
Well, for one, imagine being able to create even more accurate models for predicting disease outbreaks, being able to allocate resources more effectively, maybe even prevent pandemics.
Wow, that would be incredible.
Or how about developing much more sophisticated financial algorithms, ones that can adapt to changing markets, make smarter investments, that kind of thing.
Okay, now that's some next level stuff right there. High stakes math.
And it goes beyond that. Think about social networks, the way information spreads like wildfire online. You can analyze that using BRWs too. Understand how ideas, trends, even misinformation, how they jump from person to person, from network to network.
So by diving deep into this abstract math, by exploring the strange world of 8-dimensional branching random walks, we're actually equipping ourselves with the tools to understand the real world in a whole new light.
Exactly. And that's the beauty of this kind of research. It might seem purely theoretical, even a little bit esoteric at first.
Okay, I'll grant you 8 dimensions is a bit out there.
Sure. But by embracing that complexity, by really grappling with those abstract concepts, we open up these incredible new avenues for understanding the world around us. And who knows what other hidden dimensions are out there just waiting to be explored.
It makes you think, what other complex systems, what other seemingly chaotic processes might we be able to map and analyze using similar mathematical tools? I guess that's something for our listeners to ponder, right?
Exactly. Leave them with a little something to think about.
Well, folks, we've journeyed from the depths of eight-dimensional space to the spread of diseases, the fluctuations of the stock market, even the evolution of language, all in an attempt to understand the strange and wonderful world of branching random walks. It's been a wild ride, but that's all the time we have for today's deep dive.
Ready for a deep dive? Today, we're taking on branching random walks. Imagine a random walk, but instead of one path, it's constantly splitting, like a tree with infinite branches.
And not just any tree picture that's happening in 8 dimensions. We're going to untangle a paper that looks at the chances of these 8-dimensional trees not bumping into each other.
So we're talking non-intersection probability. Catchy, right?
Definitely. And it gets even better because this all ties into some fundamental mathematical concepts. Green's function, for instance, which helps us get a handle on how these walks behave over time.
Okay, before we get lost in the branches, let's rewind to the basics. Simple random walks. Basically, you're taking steps randomly, forward or backward, equal chance. Now picture this on a line, then a grid, then in 3 dimensions.
And as you bump up those dimensions, the odds of 2 walks actually intersecting, well, that changes a lot. More space to avoid each other, you see. For simple random walks, things get super interesting in 4 dimensions.
Right, that's the sweet spot where the expected number of times they cross paths grows logarithmically. But this paper, we're talking branching random walks, and their magic number is 8 dimensions.
Exactly. And to wrap our heads around these intricate structures, we need to think about infinite invariant trees.
So instead of a straight line or a grid, we're picturing our random walks happening on these massive, never-ending trees. What do these trees even look like? Paint me a picture.
Picture a central spine that goes on forever in both directions. Now, branches shoot out from this spine, and each of those branches can sprout more branches and so on infinitely. You get this incredibly complex structure that's self-similar at every level.
Like a fractal, where every little piece looks like a mini version of the whole tree.
Exactly. Now, imagine a tiny ant, maybe a bit tipsy, dropped on this infinite tree. It takes random steps along the branches. That's your branching random walk.
Okay, I think I'm getting it. We've got our infinite trees, our tipsy ant on a random scroll. What were the researchers trying to figure out about these walks in 8 dimensions?
Their goal was to figure out the probability that 2 of these walks, starting from the same point, would never collide in that 8-dimensional space.
Like, what are the chances our 2 tipsy ants starting at the same spot somehow manage to never bump into each other, even on this massive sprawling tree?
You got it. And to crack this, they used Green's function. They found a link between the probability of these walks not intersecting and how Green's function works in 8 dimensions.
We've mentioned Green's function a few times now. Can you remind us what it represents in this scenario? Why is it so important here?
Think of it as a measure of influence. Green's function tells us how much one point on the tree can influence other points, taking into account all the possible paths our random walk can take. The researchers discovered that the probabilities of our walks not colliding is directly related to how quickly Green's function fades away as the distance grows in this 8-dimensional space.
So Green's function is like a trail of breadcrumbs, helping us trace the influence of one point on another, even in this mind-boggling 8-dimensional setup.
Precisely. It's like finding a secret passage within the branches of our infinite tree.
This is already pretty mind-blowing, and we're just getting started. The paper goes on to derive a magic formula that links this non-intersection probability to other aspects of branching random walks.
Right. And this formula is where things really get interesting.
Lead the way. What's this magic formula all about?
Here it is. East E 0 0 0 0 E 0 0 0 0 1. Now before your eyes glaze over.
Too late. Just kidding. But seriously, can we break this down? I see those indicator functions. Those are like mathematical truth tests. Yeah. They spit out a 1 if something's true, a 0 if it's false.
Spot on. Let's see what those truth tests are looking at. The first one is checking if these 2 pieces of our walk, T0 and T, are totally separate. No overlap, no intersection at all.
And the second one checks if the walk, T, ever circles back to where it started, point 0, within a certain time frame represented by 2's.
Exactly. We're interested in whether the walk revisits its starting point during that time. The last bit of the equation, hashtag TDARN, that's counting something.
Looks like it's tallying up the times, those walks, TZR, T and Arn actually do cross paths. So this magic formula is telling us that the expected value of this whole shebang, those truth tests, multiplied by the number of intersections equals 1. But wait, how does this help us grasp that non-intersection probability we're after?
That's the magical part. This formula creates a link between the probability of no intersections represented by those truth tests and the expected number of intersections. It's counterintuitive, but incredibly powerful.
I see. If we can somehow figure out the expected number of times these walks intersect, this formula gives us a back door to understanding the chances of them not intersecting. It's like figuring out a puzzle by looking at its inverse.
You got it. And this is where the paper dives into some seriously impressive mathematical acrobatics. To get a handle on this expected number of intersections, they bring in something called a depth-first queue process, or DFQP.
A depth-first queue process. Sounds like something you'd hear in computer science, not pure math. Tell me more.
It might sound intimidating, but it's actually pretty intuitive. Imagine exploring a maze. You want a systematic way to check every single path, right? You'd go as far as you could along one path, then backtrack to the last unexplored turn and keep doing that. That's the essence of a depth-first search.
So the DSQP is like a roadmap of that maze exploration, carefully recording every turn and dead end.
Exactly. It encodes the structure of the maze, how many paths branch off at each intersection, the distances between them, all of that.
Okay, I'm with you so far. But we're not dealing with actual mazes, are we? We've got these abstract 8-dimensional trees and our branching random walks. Where does the DFQP fit into all of that?
That's where the real ingenuity kicks in. The researchers cleverly use this DFQP to represent the structure of our infinite trees. By studying the DFQP, they can estimate the expected number of vertices, or branching points, in the tree at a certain distance from the starting point.
It's like using our maze map, the DFQP, to figure out how many intersections we'd likely encounter as we move further away from the starting point. And since each intersection could be a potential collision point for our random walks, we're getting closer to understanding that non-intersection probability.
Precisely. It's about understanding the geometry of these walks within that 8-dimensional space. And the DFQP is our tool for that. Of course, analyzing the DFQP itself is no walk in the park.
I bet. That sounds like some pretty intense math.
It is. But to make things a bit more manageable, they use a clever trick. Concentration of events. Instead of trying to analyze the whole walk at once, they focus on specific things, like the number of vertices at a particular distance. They prove that these events tend to cluster around a specific range, simplifying things significantly.
So it's like zooming in on certain details of our map and proving that those details accurately represent the larger structure.
Exactly. This lets them calculate very accurate approximations for the expected number of intersections, which takes us closer to our elusive non-intersection probability.
This is brilliant stuff. But I feel like there's got to be more to this story. Didn't they have to deal with some assumptions they made early on in their analysis?
You're sharp. That's right. One key assumption involved what we might call the past side of the tree. Basically, they initially assumed one part of the walk never returned to its starting point. It's a simplification that helps at first, but for a complete picture, it needs to be addressed.
Okay, so how do you go about removing such a fundamental assumption without bringing the whole analysis crashing down?
This is where their ingenuity really shines. They introduce a weighting factor. Instead of only considering trees where that past side never touches the starting point, they consider all trees, but assign a weight to each based on how many times it touches base on that past side.
So the trees where the past side hits the starting point more often get weighted more heavily, evening things out.
Exactly. This elegant weighting system lets them account for those previously ignored trees without scrapping all their earlier work. It's like reinforcing a bridge while still allowing us to cross it. Impressive stuff.
It really is. They've dealt with those tricky assumptions, brought the past of the walk into play. Where does this winding path lead us next?
This is where things get even more interesting. This is where they introduce us to branching capacity. And you'll never guess where that leads.
You're going to make me wait, aren't you? All right, hit me with it. What is this branching capacity and what secrets does it hold?
So branching capacity, it's basically a way to measure the size of a branching random walk. How much of that 8-dimensional space it manages to explore. Think of it like this. Each branch on our infinite tree, that's a possible path, right? Branching capacity captures how much path space our walk covers.
It's like putting a number on how much ground our tipsy ant covers as it stumbles around on this infinite tree.
Exactly. And here's where it gets really interesting. This branching capacity, it's directly connected to that non-intersection probability we've been talking about.
Hold on. We started with these branching random walks, wandered into Green's function territory, navigated that whole depth-first queue process, tackled those assumptions, and now branching capacity. And it all circles back to our original question about the probability of these walks not intersecting.
You got it. It just goes to show how elegantly these abstract concepts are connected. It's beautiful, really.
It really is mind-blowing. So what's the connection? What did the researchers find out about branching capacity and how it relates to this probability?
They proved a weak law of large numbers for branching capacity. Basically, they showed that as the branching random walk keeps growing, its branching capacity, once it's properly normalized, approaches a particular constant value. And you know what? This constant value is directly linked to the constant we see in that formula for non-intersection probability.
So they've uncovered this deep link between the long-term size of our walk, measured by its branching capacity, and the likelihood of two walks never bumping into each other. It's like saying the more path space one walk covers, the less likely it is to run into another walk.
You've got it. It's a really cool insight, and it highlights the profound connection between these seemingly different ideas. And to fully appreciate this, it helps to think about those simpler random walks we talked about earlier.
Okay, back to basics. What's so special about simple random walks in 4 dimensions again?
Right, so in 4 dimensions, which is the critical dimension for those walks, there's a similar result. It connects the capacity of a simple random walk's range to a constant value. This capacity, just like branching capacity, is all about how efficiently the walk explores its space.
So this paper is essentially finding a similar connection, but for branching random walks in their own critical dimension, 8 dimensions. It's like they've found this hidden parallel between these two types of random walks, each operating in its own dimensional world.
Exactly. They've shown that this relationship between capacity and non-intersection probability, it's not just a fluke. It holds true even in the more complex world of branching random walks in 8 dimensions. It speaks to the elegant math underlying these random processes.
This is incredible. We've gone through so many layers of complexity, yet there's this underlying elegance tying it all together. But I have to ask, beyond the sheer beauty of the math, are there any broader implications of these findings? Why should we care about the capacity of these abstract random walks?
The age-old question. So what? It's what gets mathematicians going, right? Beyond the inherent beauty of it all, understanding the geometry of these branching walks, especially in 8 dimensions, has major implications for other fields of math and beyond.
You have to elaborate on that. What other fields are we talking about?
Well, for one, this research could provide new insights into problems related to percolation theory.
Percolation theory. That's a blast from the past. Remind me what that's all about again.
Imagine pouring water onto something porous, like a sponge. How does the water spread? How do these connected clusters of wet spaces form? That's percolation theory, the study of how connected clusters emerge in random systems.
Right, I remember now. But how does that relate to our branching random walks?
Think about it. Each branch of our tree, it's like a possible path for the water to flow. The branching capacity, in a way, reflects how well the water can seep through or percolate through the material. So understanding these branching random walks, especially in higher dimensions, could give us new tools to analyze and really understand those percolation processes.
It's like we've stumbled onto a mathematical Rosetta Stone, helping us decode the language of complex systems across different fields.
Exactly. It just goes to show the power of abstract math to uncover secrets about the world around us, even in areas that seem completely unrelated. This research opens up new avenues for exploration, not just in mathematics, but potentially in physics, computer science, anywhere we're grappling with complex systems. It reminds us to keep pushing the boundaries, to venture into the unknown, and appreciate the beauty of mathematical discovery.
Makes you wonder what other mathematical mysteries are out there, just waiting to be solved. What other hidden connections are waiting to be found? It's truly an exciting time to be exploring these mathematical frontiers.
It really is. This paper, with its exploration of branching random walks and their fascinating properties, is a perfect example of the power and the beauty of mathematical inquiry.
I'm still trying to wrap my head around the fact that these random walks, these abstract mathematical things, could have such a big impact on other fields.
It really shows you how interconnected math is, how something that seems niche can suddenly shed light on something totally different.
It's like that saying, mathematics is the language of the universe, or something like that. I'm not being off track. We were talking about the bigger picture of this research. You mentioned percolation theory, but are there other areas where understanding branching random walks could be useful?
Absolutely. Think about certain physical systems. Imagine particles moving randomly, branching out, interacting with each other. This research gives us a way to analyze those interactions, figure out how clusters form, maybe even predict how the system evolves over time.
So are we talking about things like, say, how epidemics spread, or how gases behave, or even how information flows through a network?
Exactly. Those might seem totally different on the surface, but underneath, they share a structure that we can model and analyze using these tools from branching random walks. It's all about recognizing those hidden patterns, the underlying math that connects them.
This is also fascinating. It's like this paper has opened up this whole new way of seeing the world, all these hidden connections and mathematical structures.
It really has, and it speaks to the power of curiosity, you know?
Yeah.
It's important to keep asking those fundamental questions, even if we don't see a practical use for the answers right away.
Because who knows what we might find along the way? Maybe a whole new branch of mathematics, a new law of physics. Who knows?
Exactly. That's the beauty of science. Sometimes the journey is just as important as the destination.
Well said. This deep dive has definitely shown us that. We've waded through some pretty complex math greens function, depth first cube processes, branching capacity, and we've uncovered these amazing connections to things like percolation theory and the behavior of complex systems.
It's been quite a journey through the world of branching random walks.
And I'm so glad you were here to guide us through it. You've explained these complex ideas with such clarity and, well, infectious enthusiasm. Thanks for taking us on this ride.
It's been a pleasure. But remember, this is just the beginning. There's a whole universe of mathematical wonders out there. Keep asking those questions. Keep looking for those connections.
And for everyone listening, we want to hear from you. What really clicked with you today? What new questions came up? Join the conversation in the comments. And until next time, happy exploring. All right, everyone, buckle up, because we are diving headfirst this time into a world where probability meets infinity.
Yeah.
The utterly fascinating realm of intersections of branching random walks on Z.
Okay.
We are going deep, deep, deep into the weeds of a research paper that asks a question that is so simple
Okay.
and yet profoundly complex.
Yeah.
What are the chances that two branching random walks, those infinite, ever-expanding paths, will never cross paths in 8 dimensions?
Right.
Expert speaker, this is some high-level math we're dealing with today.
It is.
Before we get totally lost in the weeds,
Yeah.
can you set the stage for us?
Sure.
What is it about 8 dimensions that makes it so special in this context?
Well, I mean, what's really fascinating about this research is that it kind of gets at this critical turning point in the behavior of random walks, right? So you can imagine that the probability of two walks intersecting changes dramatically depending on the dimensions we're working with. And so 8 dimensions is really where something very unique happens with these branching random walks.
It's like 8 dimensions is where the rules of the game completely change.
Exactly.
But before we jump to 8 dimensions, the paper starts out with a more familiar concept, the simple random walk. Can you remind us what that looks like?
Yeah, so a simple random walk, I mean, you can just imagine a point hopping randomly on a grid, right?
Yeah.
And the paper uses this classic example of the drunkard's walk.
Okay.
So, you know, each step is random, but over time you can calculate the probability of that point ending up at some specific location.
Okay.
And so how this walk behaves, how likely it is to intersect with another walk, changes dramatically depending on the dimensions of the grid.
So in one dimension, it's like two people walking on a tightrope. They're bound to bump into each other eventually.
Exactly.
But in 2 dimensions on a flat surface, there's more room to maneuver.
Right.
So it's less likely.
Exactly. And as we increase the dimensions, right, we give these random walks more space to spread out, the probability of intersection decreases even further.
Okay.
And so mathematicians use this tool called the Green's function to actually map out these probabilities.
Okay.
So think of it as like a probability heat map
Right.
that shows the likelihood of a walk reaching a certain point.
So the Green's function gives us a visual representation of how that probability kind of spreads out like ripples in a pond.
Precisely. And the paper delves into how this Green's function decays, how quickly that probability drops off as we move further from the starting point.
Right.
And they have these, these equations like GG1's GD2 plus O1's D to describe this decay.
I know we've got some math whizzes in our audience.
Yeah.
But for the rest of it, if I try, can you unpack that equation a little bit? What's the key takeaway there?
Yeah, so essentially this equation's telling us that the Green's function, right, that's represented by GD at a point Z, decreases as the distance from the origin, that's that Z, increases.
Okay.
And the rate of this decrease is determined by the dimension, that's D.
Okay.
So the higher the dimension, the faster the probability fades away.
So in higher dimensions, those probability ripples, they die out much faster, making intersections less likely.
Exactly. And the paper emphasizes that this decay is absolutely crucial for understanding the behavior of both these simple random walks and, more importantly, these branching random walks.
Which brings us to the heart of this research. Branching random walks.
Mm.
It's like our lone drunkard suddenly has a family and they all embark on their own random journey.
Precisely. We're moving from a single path to a tree-like structure where each point can branch out into multiple new walks.
So instead of one Green's function, we now have like a whole forest of probability heat maps, each branch with its own set of possibilities.
And that is where this concept of the infinite invariant tree comes in.
Okay.
So you can picture a tree with an infinite spine, and at each point on that spine, you have more finite random trees branching out.
Okay.
And this structure underpins this entire concept of branching random walks.
So it's like a fractal-like structure, just a mathematical representation of endless possibilities.
And one of the remarkable properties of this infinite invariant tree is that it's shift invariant.
Okay.
Meaning that no matter where you start looking at this tree, the overall structure, the probabilities, they all remain consistent.
It's like zooming in on a fractal. The same patterns repeat at every scale.
Precisely. And so this shift invariance is a crucial property that these researchers exploit when they analyze these branching random walks.
So we have our stage set, right? We've got branching random walks, each with its own Green's function unfolding on this infinite shift invariant tree.
Yeah.
Now, with all of this, what is the million-dollar question that the researchers are trying to answer?
The core question is, what is the probability that two independent branching random walks, two of these sprawling family trees of random walks, will never intersect?
It's like asking, in a universe of infinite possibilities, what are the chances that two paths will forever remain separate?
Yes, and this question becomes particularly intriguing in 8 dimensions because that's where the answer takes a dramatic turn.
8 dimensions. It's like the twilight zone of mathematics.
Yeah.
But why? Why is 8 the magic number for branching random walks?
Yeah, so 8 dimensions turns out to be this critical dimension for these types of walks, right?
Okay.
So it's this point where the expected number of intersections between two walks shifts dramatically.
Okay.
So below 8 dimensions, intersections are almost inevitable.
Okay.
But at 8 dimensions and above, the probability of these paths never crossing becomes much, much more likely.
So it's a tipping point, like a fundamental shift in the behavior of these walks.
Exactly.
And the researchers in this paper, they actually managed to calculate this probability.
They do. And they give us not one, but 2 answers, each with its own sort of level of detail. So theorems 1 and 2 are kind of the heroes of this story.
Okay.
Theorem 1 gives us this general order of magnitude for this probability, showing that it decreases as a power of the logarithm of the number of steps in the walks.
So the longer the walk, the less likely they are to intersect, but in a very specific way. It's not a linear relationship. It's tied to the logarithm.
Exactly. Now, Theorem 2 zooms in even further.
Okay.
It provides what are called precise asymptotics, so essentially a very, very precise description of how this probability behaves under certain conditions.
Okay.
Particularly when we focus on the walks never hitting the starting point again.
It's like they've taken this high-resolution snapshot of this incredibly complex system.
Exactly.
I have to ask, what does the math look like? Is there some elegant formula that kind of captures all of this?
There is. They unveil what we might call the magic formula.
Okay.
And that is E1 ni 1 ben n ln1.
That looks deceptively simple. Can you break that down for us? What are all those symbols?
Okay. So let's start with n and bn.
Okay.
So these represent the events of our branching random walks never intersecting up to a certain point.
Okay.
N focuses on the past of one walk not intersecting with this segment of the other, and BN makes sure that the future of that segment doesn't hit the starting point of the first walk.
So they're very carefully defining what it means for those walks to truly remain separate.
Exactly.
Okay.
Now, the 1 with the subscript is just an indicator function.
Okay.
So it's equal to 1 if that event, N or Bn, is true, and 0 if it's false.
Okay.
And that just helps turn these events into something we can actually calculate with.
Okay. So they've set up these conditions for non-intersection.
Yeah.
But what about that ln? That one seems a bit more complicated.
Yeah, so Ln is really where things get interesting.
Okay.
This is a sum that essentially meticulously counts the number of times the first walk hits points on the second walk.
Okay.
But there's a catch. It only considers intersections within a specific range, determined by these randomly chosen points, which are denoted by Fron and Orn.
So LEN is like this careful accountant, like tallying up the potential intersection, but within a very particular window.
Exactly. And what's remarkable is that by setting up this equation in this really clever way, the researchers demonstrate that, on average, there's only going to be one last intersection between these two branching random walks.
Okay.
And to do this, they use this technique called a last exit decomposition.
Okay.
So imagine, like, tracing the walks backward
Right.
from a potential point of intersection.
It's like rewinding those drunken journeys and realizing that once those paths diverge in 8 dimensions, they're unlikely to ever find their way back to each other.
Precisely. And so this magic formula really encapsulates that idea beautifully.
Yeah.
But to prove that formula requires some serious mathematical machinery.
Okay.
And this is where they introduce this concept called depth-first queue processes, or DFQPs.
DFQPs. Now that sounds intimidating.
It might sound complex, but the idea is actually quite intuitive.
Okay.
So imagine you want to analyze a tree.
Okay.
But trees, with all their branches, are very, very difficult to represent mathematically.
Right.
DFQPs give you a way to encode that branching structure into a more manageable linear sequence of numbers.
So it's like taking that tangled family tree and like neatly organizing it into a single line.
Exactly.
But how does that encoding actually work?
Yeah. So imagine you are like walking along the edges of the tree.
Okay.
And every time you encounter a new vertex, so a point where the branches split, you add a number to your sequence.
Okay.
And that number represents how many children, so how many new branches, are stemming from that vertex.
So like a 1 would mean that the branch just continues, a 2 means it splits in 2, and so on.
Exactly. Yeah. So it's a really clever way to translate this branching complexity of a tree into this very simple linear code.
Okay, so they've got their tree translator, their DFQP. But how does that help them with these random walks that are happening on top of that tree structure?
That's the real booty of these DFQPs.
Okay.
By analyzing the properties of that encoded sequence, they can actually glean insights into the random walk itself.
Okay.
For example, they can calculate the expected number of vertices a certain distance from the starting point.
Okay.
Or the average distance between 2 randomly chosen vertices.
So it's like using the code to decipher these secrets hidden within the tree's branches.
Precisely. And remember we were talking about the Green's function acting like this probability cloud.
Yeah.
These DFQPs become crucial because they allow these researchers to approximate these Green's functions for different parts of the branching random walk.
Okay.
And this is particularly impressive because these walks don't have this nice predictable Markov property that makes the simple random walks so easy to analyze.
So they're dealing with a whole other level of complexity here.
Yeah.
But they found this tool that allows them to start to navigate it.
Exactly. And this is really just the beginning. So with the DFQPs in their toolkit, they can start to tackle this core challenge, proving that that key quantity in their magic formula, that ln that's counting the intersections, is what mathematicians call well-behaved.
Well-behaved. What does that mean in this context?
It means proving that ln is concentrated around its expected value.
Okay.
So, imagine, you're trying to weigh a feather on a scale.
Okay.
But the scale is wildly inaccurate, right? Just jumping all over the place.
Yeah.
You wouldn't be able to get a reliable measurement.
Right.
Proving that ln is concentrated is like calibrating that scale.
Okay.
It ensures that the calculations are based on a solid foundation.
So they need to be confident that ln isn't introducing just this wild degree of uncertainty into the calculations.
Exactly, exactly. And that's where things get, really interesting mathematically speaking.
Yeah.
So to achieve this, they introduced this new notation So they define these quantities like Sifly and Thich.
Okay.
Now, these might seem abstract,
Yeah.
but they represent carefully constructed expectations that are related to the structure of these branching random walks.
So it's like they're inventing a new language to describe this very intricate dance of these walks.
Precisely. And each one of those this plays a specific role,
Okay.
allowing them to break down the expectation of ln into manageable pieces
Okay.
and ultimately prove that it is concentrated.
Okay.
And that lays the groundwork for the rest of their proof.
Okay. So they've tamed ln, they've ensured that their calculations are reliable. What's next?
Right. So the next challenge involves actually tackling that magic formula. So
Yeah.
remember, it's E1 and 1B and ln 1, 1.
Right.
We proved that ln is well behaved,
Right.
but there's still this issue of dependence between ln and those non-intersection events. And
Although because they all stem from the same underlying branching random walk.
Exactly.
Yeah.
Exactly. It's like saying that the number of conversations at a party is influenced by both the number of guests and how those guests are grouped.
Yeah, yeah. Okay.
Right. So to deal with this, they have to get creative.
Okay.
So they start splitting those branching random walks into different sections.
Okay.
So the parts that are near the starting point, those are denoted by the symbol he,
Okay.
and those that are further away are denoted by s.
Okay.
So think of it like dividing up a family reunion into different generations.
Okay. Right. So they're slicing and dicing those infinite trees to try to get a better handle on these dependencies.
Precisely. And they define these new quantities,
Okay.
like un-e, which counts the expected number of intersections between the s-sections of two trees.
Okay.
And they do the same for intersections between the s and the sections and so on.
It's like analyzing those mingling patterns at that family reunion, right?
Exactly. Exactly.
Like how likely are the grandparents to chat with the grandkids and so on.
Precisely. And they introduce these other events like A's,
Right.
which checks if specific sections of those trees,
Okay.
the sections in this case, act as barriers, preventing the walks from reaching certain points.
It's like seeing if there's a big group of people blocking the doorway, preventing the different generations from mixing.
Exactly. And by meticulously analyzing all of these carefully defined events and quantities,
Yeah.
they can finally prove Theorem 4,
Okay.
which establishes this exact asymptotic behavior of that non-intersection probability, but still with those extra conditions about not hitting the starting point.
Okay, so they've wrestled Theorem 4 into submission.
Right.
But we still have Theorem 2 in our hands.
Right.
The one with those precise asymptotics. How do they bridge that gap?
Yeah. So this is where their really deep understanding of probability distributions comes into play.
Okay.
They recognize that those random variables they were using to define those ranges for ln, those odd and an error, they actually follow what's called a geometric distribution.
Geometric distribution, doesn't that have to do with those, like, how many tries until you succeed scenarios?
Exactly. Like flipping a coin until you get heads.
Right.
The number of tails before that first heads is geometrically distributed.
Okay.
And the really nice thing about these distributions is that they're memoryless.
Memoryless meaning, like, each new flip is independent of the previous ones.
Exactly. It doesn't matter if you flip 10 tails in a row. The odds of getting heads are still the same.
Right, right.
And that property becomes kind of their secret weapon.
Okay.
They exploit this memoryless nature to really simplify their setup.
Okay.
So they essentially replace those random endpoints defined by Arnon and Saran with fixed ones.
Okay.
Without actually affecting the asymptotic behavior of that non-intersection probability.
So it's like saying, instead of flipping a coin until we get heads,
Right.
let's just agree to flip it 10 times.
Exactly.
It simplifies things without changing the underlying probabilities.
Exactly. It streamlines the whole process.
Okay.
And this allows them to basically leverage the power of Theorem 4,
Okay.
but now with those precise conditions
Right.
leading them to the proof of Theorem 2.
Okay, so they've tackled Theorem 4.
Yeah.
They used it to conquer Theorem 2.
Right.
But what about Theorem 1?
Right.
That one dealt with that non-intersection probability in a more general sense.
Yeah.
Without those specific conditions on hitting the starting point.
Yes. Theorem 1.
Yeah.
This is where they have to confront this really significant hurdle, which is the lack of what's called the Markov property in these branching random walks.
Okay.
So remember how we talked about how those simple random walks
Yeah.
have this nice property where the future only depends on the present,
Right.
not on the past.
Right.
Branching random walks are more complex. The past can influence the future in these really subtle ways.
So it's like those branching paths, they carry a memory of where they've been,
Exactly.
which makes analyzing them a lot trickier.
Exactly. So to deal with this, they use this, I think, really brilliant strategy.
Okay.
Instead of analyzing the probability of non-intersection directly,
Yeah.
they shift their focus to a slightly different quantity.
Okay.
They look at a branching random walk that's conditioned to never hit the starting point at positive times.
So they're like forcing those walks to avoid the starting point from a
Indeed.
certain point onward.
Precisely. But there's a twist.
Okay.
They weight this conditioned walk
Okay.
by the number of times it did hit the starting point
Okay.
at negative times. So essentially, like before this conditioning kicks in.
So it's like saying we're interested in those walks that eventually steer clear of home,
Right.
but we want to factor in how often they visited home in the past.
Exactly.
Why weight them that way? What's the point of that?
Yeah, so this weighting is really the key.
Okay.
It creates this really clever link
Yeah.
between that more complex non-intersection probability
Right.
and an expectation that's easier to handle. So they show that the original probability
Yeah.
is what's called asymptotically equivalent
Okay.
to the expected value of this new weighted conditioned walk.
So it's like they found a more convenient measuring stick,
Exactly.
a proxy that reflects that original quantity,
Exactly.
but is easier to actually work with.
Precisely. And they prove this equivalence through this really, really clever decomposition
Okay.
based on the first time the walk hits the starting point.
Okay.
So by carefully breaking down the probability into these cases,
Yeah.
they show that each case contributes to the overall expectation
Okay.
in this very predictable way.
It's like carefully dissecting this complex machine
Exactly.
to really understand how each part contributes to its overall function.
Precisely.
But how do they actually calculate this expectation?
Right.
They're still dealing with these really intricate branching
Yeah.
random walks.
Yeah, so this is where their mathematical dexterity really, really shines.
Right.
To actually bound this expectation, which, remember, involves both this probability of non-intersection
Right.
and the number of visits to the starting point.
Yeah.
They make another really strategic simplification.
Yeah.
They shift their attention from the total number of vertices in the walk
Okay.
to just those that lie along what we've been calling the spine
Okay.
of that infinite invariant tree.
So back to that core structure, like the backbone of all those branching paths.
Exactly.
Why focus on the spine?
Because the spine holds the key to unlocking this problem.
Okay.
By focusing on the spine, they can leverage the power of the infinite invariant tree's properties,
Right.
particularly that shifting variance that we talked about earlier.
Right.
They can express the expectation as the sums related to the positions on the spine.
Oh.
And then their knowledge of these random walks in those Green's functions comes into play
Yeah.
to actually bound those sums.
So it's like they've untangled those branching paths, laid them out along that infinite spine,
Yeah.
and are analyzing them like segment by segment.
Precisely.
Yeah.
But of course, it's,
Yeah.
it's not quite that simple.
Right.
They have to meticulously consider all these different scenarios. Walks that visit the starting point often, walks that stay far away, walks that oscillate back and forth.
Right.
And for each of these cases, they use, different strategies, different tools from their mathematical arsenal
Right.
to really, really tightly bound
Okay.
their contribution to the overall expectation.
It's really a testament to their persistence.
Yeah.
Carefully examining each possibility, each twist and turn that those walks can take.
Precisely.
Yeah.
And through this really meticulous analysis,
Yeah.
they ultimately demonstrate that the expectation behaves exactly as needed,
Okay.
confirming that the original probability of non-intersection is indeed inversely proportional to that logarithm of the number of steps,
Right.
just as Theorem 1 states.
A hard-won victory.
Yeah, absolutely.
But their exploration doesn't even stop there.
It doesn't stop there.
They introduce another really fascinating concept,
Did you-
branching capacity.
Yes.
What exactly is branching capacity?
Yeah.
And why is it important in this context?
So branching capacity, denoted as BCAP,
Yep.
is essentially a way to measure the size or spread of these branching random walks.
Okay.
It's like the usual concept of capacity that we use for sets.
Okay.
But there's this really crucial difference. It takes into account the branching structure,
Yeah.
that inherent tree-like nature of these walks.
So it's not just about how much space they take up,
Right.
But it's how they spread out in that space.
Exactly.
How those branches reach out.
Precisely. And one of the things that they prove,
Yeah.
which is really remarkable, is what's called a weak law of large numbers for this branching capacity.
Okay.
So they show that the branching capacity of a branching random walk, after you scale it appropriately,
Right.
converges to a specific constant.
So even though these walks are inherently random,
Yeah.
there's this predictable
Right.
average behavior for how they spread, for their branching capacity.
Exactly. And this isn't just some mathematical curiosity.
Yeah.
Branching capacity really gives us this new lens
Yeah.
through which we can study the geometry of these really complex random walks,
Yeah.
especially in these high dimensions.
And the fact that it follows this law of large numbers,
Yeah.
it just hints at this underlying order,
Yeah,
this predictability within what seems like chaos.
absolutely.
It's incredible how this research just reveals these hidden patterns,
Yeah.
these really elegant structures within a system that's driven by randomness.
It really speaks to the power of mathematical tools, right?
Yeah.
And intuition.
Yeah.
By, carefully defining these new concepts like
Yeah.
these DFQPs and this branching capacity,
Yeah.
and by really, really meticulously analyzing these really intricate probabilities.
Yeah.
They've opened up this new window into the behavior of these fascinating mathematical objects.
Expert speaker, thank you so much for guiding us through this incredibly complex and fascinating world of branching random walks.
My pleasure.
Your insights have been just invaluable.
Oh, glad to hear it.
And to our listeners, the intrepid explorers of knowledge, we hope that this deep dive has sparked your curiosity and inspired you to keep seeking out those hidden patterns,
Absolutely.
those unexpected connections that make the world of mathematics so captivating.
It's a beautiful world out there.
Until next time, keep asking questions and keep exploring.